Extend 4.1 as well, has all the features. And also over the last year, it's been ported to OpenFoam v18.12, v19.12, and 7. Just an asterisk or caveat beside the official OpenFoam versions. Currently, the tutorials, you just need to manually tweak them to get them to run. There is a branch where I've automated it, but it's yet to be merged. I'll probably merge it over the next month or so. So solids4Foam can be downloaded at this address here. It's at a Bitbucket repository. It's fully public. Up until relatively recently, it was public, but you just had to send me an email first, and I added you to it. But I've removed it now, so you can still email me, and I'll add you if you want to be a member on it. But you can publicly download it without a Bitbucket account from this link. So you can put it anywhere. I normally just put it one back from my run directory. This will download it using Git. And then you'll end up with a folder called solids4Foam release. You cd inside that, and there's an included all wmake script for compiling it. So run that, and then 5 minutes later, when it completes, if you write solids4Foam-help, that's the name of the solver, you should see this if it was installed correctly. It'll just say the usage. So now you're all set up. So that's installing it natively. So if you have Foam Extend 4.0, 4.1, or any of the OpenFoam versions, that should work. If you're using Docker, so if you're not familiar with Docker, it's like a lightweight virtual machine. So the idea is if you're working on, for example, Windows, it might be convenient to install via Docker. So it's essentially, I've created these Docker images out of Ubuntu's. So it's like a lightweight version of Ubuntu. So I myself use a Mac and Ubuntu and sometimes Windows, so it can be convenient to use Docker because the same setup and code will run on all systems. So once you've Docker installed from the official website, you can open a terminal, or if you're on Mac or Linux, or PowerShell on Windows, and you can pull down a public solids4Foam image. From here, this is my Docker Hub account. So that'll download a working version of solids4Foam built with Foam Extend 4.0 built on top of Ubuntu 18.04. Once you've downloaded that, you can create a container, and a container it's basically like a running version of one of these machines. It looks a little bit complicated, but it's just setting up shared directories. Because this is its own independent machine or computer that runs within your computer, you have to explicitly tell it how you can share in between, which folder is shared between both of them. And then you can run this command to start it. I'll show an example of that later once I switch to the terminal. Once you've logged into that, you can just check solids4Foam command works. And you can type exit to get back out of the Docker container. So both of those are public. You can try it now. You can download it if you want. I'm not sure if anyone's following along, but if you want, you can try download it. If your internet's fast enough, you can download it and catch up. But either way, as I said, you'll be able to follow along afterwards from the PDF and a recording, as far as I know. Within the Docker, it's just the bare bones of Ubuntu to run solids4Foam. So if you want Emacs, for example, you have to install it using sudo apt-get. And this is the default shared folder. Okay, before I change to the terminal, I'm just going to talk to you a little bit about solids4Foam, just as an overview. So back during my PhD, which I completed in 2012, I was working on solid mechanics in OpenFoam, one of few people. But I found it interesting, so I shared some of the solvers I developed in Foam Extend under the solid mechanics folder. I was fortunate to work with lots of other smart people as well. So at the time, Željko Čuković spent some time in Dublin. He was working on FSI as well. So it included this ICO, FSI, non-lin, elastic, some very long name FSI solver. And that was fine. Since then, Željko released this Extend Bazaar FSI, which works great. And then since then, myself and Željko had been, and others had been working on this solids4Foam as a kind of the latest version or toolbox based on all of these codes. And with solids4Foam, I'm trying to emphasize that it should be easy to use, to understand when you go into the cases and the code. And then I guess for developers like myself, is easy to maintain and extend. So I'm trying to put an emphasis on nicely written code that's easy to use. So far, all the features are available in 4.0 and 4.1 Foam Extend, and most features are available in the open foam versions. And because some things aren't exactly like for like between the versions, sometimes you can find a replacement and sometimes you can't. So for example, there's the block coupled framework in Foam Extend. Currently doesn't exist in these official open foams, but you can figure out smart ways to port them. So everything can be ported if it needs to be. The general idea of solids4Foam is to just have one solver called solids4Foam. Obviously, just to mention as well, the name was inspired by waves to foam and swag for foam. It rolls off the tongue, so that's good. So solids4Foam is just one solver. And within this solver, it's essentially like a kind of a shell of a solver, like an abstract solver, because inside it, it creates an object of class physics model. And the physics model can either be a solid or a fluid or a FSI simulation. So the typical open foam approach is to have a different solver for every physics problem. Whereas this is an alternative approach. This is where we just one executable, and at runtime we use a runtime selection mechanism to decide are we going to run a solid or a fluid or FSI, which is specified in the case itself. The benefit of this is when we go to FSI, if I want to have one type of solid model coupled with another type of fluid model, say like a pimple foam coupled with like a elastoplastic solid model, I don't want to have to copy and paste code to write a new solver. So copying and pasting is bad. It leads to errors. So this way I can just automatically couple any solid and any fluid into FSI. So that's the benefit. The disadvantage is all the fluid models in OpenFoam have to be copied and pasted to into a new fluid model class. So there's pros and cons. So in solids4Foam, you have something called piezo fluid, and that's just piezo foam, which is wrapped up into a class that can be called. And similarly, simple fluid or interfluid, etc. So it's pretty quick if you want to deport them, but you do actually have to copy the code. It's not directly calling the OpenFoam solvers. Within the solid models, obviously most people at this conference will be fluid dynamics people, so you're maybe less familiar with it, but just like in fluids, there's very many different solution approaches, say for example, compressible, incompressible, kind of explicit or implicit. We have the same in solid mechanics. So we have small strain approaches like the original solid displacement foam, or large strain approaches using different mathematical frameworks. So total Lagrangian or updated Lagrangian. And we have different solution methods, so coupled or segregated or explicit or etc. etc. And in fluids, often the critical thing to get accurate predictions can be the choice of fluid of turbulence model. So an analogy of sorts in solids is the constitutive model. So the turbulence model in fluids is giving you your definition of stress or Reynolds stress or deviatoric stress. So in the same way, the constitutive model in solid mechanics gives the definition of stress as a function of your velocity or pressure, or more commonly in solids, your displacement field. So you might be familiar with linear elastic or Hookean elastic, it's called. That's just the most simple approach. But you might have plasticity, you might have poroelasticity, you might have viscoelasticity, etc., etc. Also, you could write a wrapper if you wanted to call a constitutive model, a user subroutine from Abacus or ANSYS. You could write a wrapper to call one of those as well. So you just give it in your kinematics, your deformation, your velocity field, essentially, and then this class will give back a stress. There's also large strain equivalents as well. And then with FSI, the current methods in solids4Foam are using the same as Extend as Art. They're using this partitioned approach where you solve for the fluid, then the solid, then the fluid, then the solid, and you keep iterating until it converges in a time step, and then you go to the next time step. You could just do one fluid, one solid, which is called a weakly coupled approach, and then go to the next time step. There's different ways to do that coupling. There's fixed under relaxation, so you calculate the fluid flow, the velocity and the pressure of the fluid. That will give you a certain pressure distribution and shear stress distribution on your solid. Then you will interpolate that or map that to the solid, solve the solid. The solid will then deform or move. So the deformation of the solid, you pass that back to the fluid to move the fluid mesh. Because the solid now moved, you need to move the fluid mesh. So then you go back to the fluid and you solve it again, and you keep iterating between that. When you're passing these pressures or forces or displacements, you might use under relaxation, to promote convergence. So there's this Atkins or Aitken's method, which is commonly used, and then this inverse quasi-Newton method, which is also used, developed by de Groote and Baat. This seems to be the state of the art. Not necessarily the particular implementation in solids4Foam, but in the literature, this seems to be the state of the art. Just to comment on coding style, within OpenFoam, not many people know, but OpenFoam Foundation actually sets out a coding style guide. So style is not something, I guess, the average PhD student cares about too much when they're writing their solver. They will just write their solver and they want to get it to work. And then they might say, if you tell them about style, that, oh, they'll go back and change that once the solver's working. But generally, once the solver's working, people don't go back and change anything. So it is important, though, because if you stick to a consistent style, then reading code becomes much faster and easier, and because you know what to expect, where the brackets should be lined up and things like that. So it is important, and going back to this mantra of maintaining, easy to maintain and extend, it's important. So the code on the left is perfectly legitimate C++ OpenFoam code. And if there was some project that defined the style as that would be fine, but OpenFoam says this is not OpenFoam style. So this is the equivalent. So it's a lot to do with alignment and spacing between characters and operators. Many C and C++ projects use this style of if, but OpenFoam has decided on this. It's a little bit arbitrary, but if everyone sticks to this, it makes it much easier for everyone to follow code. And finally, before getting to the terminal to actually play with solids4Foam, I'm just going to comment on finite volume versus finite difference versus finite element. So OpenFoam is obviously based in, well, mostly in the finite volume method. You can implement the other ones, but that's the primary goal of OpenFoam. So in solid mechanics, most people know the finite element method is the main used method, but you can use any of these. So solids4Foam is using the finite volume method. So first came the finite difference method, and that was generalized to the finite volume method. So generalized in terms of geometry and topology. So by geometry, I mean, now we can have complicated shaped cells. In topology, they can be connected in all strange ways. So each cell doesn't have to have a fixed number of neighbors. So it was a generalization of the finite difference method. But actually, it's an entirely different philosophy. So the finite difference method is taking our governing equation in differential form and applying it at each point. So at each point, we're summing the fluxes going into that point, and we're solving it point-wise. The finite volume method is entirely different philosophy. So we're taking actual finite volumes and we're integrating over these. We're summing fluxes going through surfaces. So even though they come from the same place, or the finite volume method comes from finite difference, it's quite different in its philosophy. And for simple grids, yeah, of course, and simple finite volume schemes, you get the same discretization exactly. Finite element, on the other hand, they start with the point form and they integrate that over a volume. So if we take this node here, the domain around that will be all the elements adjacent to that. So they integrate, or they apply their conservation equation in an average volume sense over this volume. So that's just another philosophy. It's just a different way to solve partial differential equations. There are many differences. We could spend an hour talking about the differences and similarities, but they're essentially just different ways to solve partial differential equations. Okay, now to get to the first test case. So my first test case using solids4Foam. So the first test case I'm going to look at is this hot sphere test case. So it's basically a pressure vessel. So it's a sphere with a certain thickness wall. On the inside, I'm going to apply a pressure that's a function of time. So it's just the time in seconds divided by 5 in megapascals. So it's just a linearly increasing pressure. Starts at 0, increases over time linearly. The temperature, I'm also going to increase linearly on the inside. So it's getting hotter and higher pressure on the inside. On the outside, the pressure is 0, so it's like just free air. And then I have a coefficient of heat transfer coefficient. So it's losing heat proportional to the temperature of the surface. This is the mesh I created. There's no block mesh in this. I'm actually using a mesh that I've temporarily stored in the fluent mesh format. Strangely, when I went to make a mesh of a sphere, most of the versions of OpenFOAM, the way they apply curves cannot do spheres exactly. So one of the versions of OpenFOAM, I think it's the foundation version, and their block mesh can actually exactly reproduce spheres, but the other ones can't. This problem is actually 1D. 1D in the sense if I plot any solution field from A to B here across the wall thickness or any radial line, it'll always give me the same answer. The reason I've done a quarter here is just to demonstrate it in 3D. It looks a bit nicer as well, and also just to show parallel scaling efficiency. The results are expected to look like this. So temperature at, I think this is at 5 seconds, yeah. It'll vary from 500 on the inside to whatever that is on the outside. I ran it with 4 different meshes. I compared it to Abacus finite element and some other solution from literature. So not too exciting, the temperature distribution, but the von Mises stress distribution. So it's one of the definitions of a definition of equivalent stress is a little bit more interesting. So this is why this is a benchmark case, because it's more nonlinear, the distribution across a small thickness of wall. So it's a good check on your numerical schemes. So if you take any one of these points, say the big circle, as I refine the mesh, you can see it's, you can approximately see it's a second order, right? The equations that are solved, you've conservation of momentum. So just like in fluids, sum of the surface forces plus the body forces equals mass of acceleration. Your energy equation in heat form, so sum of all surface heat fluxes equals rate of change of internal energy, which is this kinetic energy term, which typically is small or dropped out or drops out. And then the definition of stress, this is your standard Hooke's law if you're not familiar with it. But when you have thermal contraction or expansion, there's an extra volumetric term, like a pressure generated by the changes in temperature. The solution methodology in the solver that we're going to use. So this is within the solid model that we're going to choose for this case. It's going to go for each time step. It's going to do a loop. So it'll solve the energy equation, T, holding any D terms constant. Then it'll solve the D equation holding D terms constant, and then it'll iterate between them. You could implement a coupled version of these as well, but typically that's not needed in these cases. Okay, at this point, I'm going to switch over to the terminal. So the next few slides, if you want to follow back later, are basically going to, the slides will show you all the commands you have to type. So I'm just going to copy the tutorials, go in, run the different commands and open PowerView. So I'm going to skip back between the terminal and here. So these slides are just going to remind me what I'm going through. Okay, so if I go to the terminal, I will make my text a bit bigger. If nobody says, if the chair doesn't say anything, I'm going to assume my my font is big enough. Okay. No, I think it's good enough. Okay, good. Okay, so I've downloaded solids4Foam. I just renamed it OpenFOAM 15 just to keep it separate. So if I type ls dash all, which is my default alias for ls, this is what solids4Foam looks like inside. So it's a similar structure to OpenFOAM in that we have applications. Inside applications, we have solvers and utilities. Inside solvers, we have just one solver, solids4Foam. There's some companion utilities for setting up cases. We also have SRC. Inside SRC, we have 2 libraries. We have solids4Foam models. That's pretty much the main solids4Foam library with all the solid models and fluid models and FSI procedures. And then I've just taken out the block coupled solution procedures into a different library. We'll come back and look through some code later. We have tutorials. Inside tutorials, we have them broken down into solids, fluids, and fluid-solid interaction. Fluids is just a few example ones because obviously you're not going to use solids4Foam just for fluids, but it's just to show you how it works. There's lots of solid ones and there's a few FSI ones as well. We're going to look into that a bit further. Documentation, essentially these slides are also presented in Markdown format as well. So if you just download a Markdown viewer, you can open those up and they're all hyperlinked. So you can go through these slides there as well. Third party, there's a couple of packages that get download. Actually, there's only one in the master branch, which is Eigen. So Eigen is just a header library for linear algebra and things like that. That's used a few places in the code. So that gets automatically downloaded when you run allwmake. A few other things, you'll see the allwmake and allwclean scripts. It's a Git repository, and there's a Docker file here as well. So when a commit gets pushed to Bitbucket, it automatically gets built and checked, and then also there's a hook on Docker Hub which will automatically pull it and build it as well. But if you download this and you run Docker build, it will generate an image from this as well. Last thing is files to replace in OpenFOAM. Sometimes there's some bugs or changes in the code required for some of the OpenFOAM solvers. Generally, they get fixed by the next version, but temporarily they get put here. So all of these changes might not be needed in each version of OpenFOAM, but it's just files showing the changes. So when you run allwmake, if it finds the change hasn't been made, it will just stop and print a warning. It won't replace it. It'll just tell you might want to replace it yourself. If you don't want to, you can just comment it out, but there might be some test cases that won't work if you don't replace them. If I go into the tutorials, if I go into solids first, because that's where we're going to start. So they're broken down into different types of solid behavior. So you have linear elasticity test cases, hyperelasticity, which is it's like large strain or finite strain. So then we have elastoplasticity, so permanent deformation, fracture, examples using multiple materials, pore elasticity, thermoelasticity, and viscoelasticity. So we're going to thermoelasticity. And you'll see there's 4 test cases, and we're going to go into hot sphere. So all the test cases have an all run script. So you can go in and just run like this, and that will run the commands required for the test case. So I'll let that work in the background. If I open my all run script here, you can see it. In this case, it just converts this hot sphere from a fluent mesh format to the OpenFOAM format, and then runs solids4Foam. This was, as I said, actually created in OpenFOAM, but since it requires a particular version of block mesh, I just found it easier to save it in the fluent mesh format. Okay, so that's running now. If I type ls, you can see there's some time steps being written. I think it goes to 5. If I tail the log, you can see the solver's running. In a while, I'll go through what the residuals mean, the way they're written out, so they're in a non-standard OpenFOAM format. So I think it has to go to 5 time steps. So if you are following along, you can try this test case. It takes about a minute. It's almost done. So if I ls first inside the constant folder, and it might be easier to go back to the slides for that, just to show the makeup. So you can see these are some of the things I've been talking about. This is just giving some tips on if you're using the Docker image. Parity is not installed in the Docker image. So what you can do is you can copy the case into the shared folder, and then you can just open up a terminal on your actual physical computer and navigate into that shared folder and open PowerView from there. So the instructions to do that are given here. So actually first I'm going to open PowerView and I'm going to look at the results. So I've set up a alias on my computer. I'm using a Mac at the moment, ParaX, just to open using the built-in PowerView to open up this case. But you can just write ParaFoam or whatever way you normally open PowerView. So when I open it up, here's the case. Turn on the mesh. If I don't skip time step 0, go back, you'll see there's two fields. So when we saw the governing equations, we saw the solver solving for displacement, which is D, and T, which is temperature. So if I just skip to the last time step, rescale, we can see we kind of have our linear distribution of 500 on the inside, 2, 3, 30, give or take on the outside, and it's all 1D. It's our temperature field. If you look at the displacement field, it tends to move. This is the magnitude. It's greater movement on the outside than the inside. But the solver will also print out a number of other fields. So sigma is your stress tensor. So this is a symmetric tensor. So you've got all your components, if you want to look at them. And you've got sigma EQ, or sigma equivalent. This is the von Mises stress. You've got the hydrostatic stress as well, sigma Hyd. So this is like pressure in the fluid, except it's the negative of it. A few other things as well. You've epsilon, that's the strain tensor. So it's symmetric tensor again. And epsilon equivalent, which is the equivalent strain. Just to comment as well, maybe it's a little confusing, but you'll see these DD fields. So some of the solid models will solve for D, so that's total displacement, and some will solve for DD. So DD means increment. So maybe we should use a small letter for D, but anyway, the convention is stuck now, so we're using a large D. So the first D means like a delta D. So delta D is the change in displacement from time step to time step. So new displacement minus the old, that's DD. So all of the solvers, will, whether they solve for D or DD, will print both of them out and calculate both of them. So if I look at DD, the pressure is changing. So DD is just the change in displacement from one step to the next. And then D is the total. So D minus the old here. So underscore 0 is old. So that's the old increment. This is the old displacement. And so difference between D and D old is equal to DD. Okay. Also, which people find a bit confusing in solids, if it's a small strain approach, so maybe you're not familiar with that, but there's kind of two main ways to model it. If you open a finite element software like Abacus, you have to choose if you want this large strain or small strain approach. It's also called a nonlinear geometry or linear geometry or nonlinear geometry approach, or MLGeom in Abacus. So if it's small strain, it means if the deformation is so small, so by so small, I mean if I take one cell, if the deformation is a small fraction of the size of the cell, then you can ignore its effect it has on the movement of the mesh. So then you solve for a displacement field on top of a stationary mesh, because the changes in volumes and areas of the mesh are so negligible, it's fine to ignore. That's called a small strain assumption. So in that case, a small strain solver, it is Eulerian and Lagrangian at the same time. They coincide, whereas the large strain solvers do need to move mesh. So we're using a small strain solver here. So to actually see the motion, you have to warp your geometry. So if you click this warp by vector button, and if I select the displacement field and press apply, then not much happens, because this is a steel cylinder. The deformation is going to be tiny, but I can rescale it. So just artificially, I can multiply all the displacements here. Power view calculated to be about 240. So I can scale it just to see what the deformation looks like on where I've ramped it up. So if I press play, you can see the pressure is increasing and the temperature is also increasing. So you can see the whole thing grows. And this is not a power view tutorial. I think there is a nice power view tutorial by Kitware. I'm not sure which day it is. But if you have these symmetric cases, you can use the reflect filter to generate your full cylinder if you want it. So you can just do 3 reflects. Yeah, so that gives you your full, just in case you have symmetric cases. And then you can slice through it in whatever way you want. to look at the results. Okay, great. So that's what the results look like in this case. Just going to jump back to the slides for a second. So you can see here, I'm just saying that if it's a small strain approach or linear geometry approach, then to see the actual deformation of the solid, you have to work the geometry. So some people get confused. They think, well, because the mesh isn't moving, it's not calculating the motion of the mesh, which is not true. So it is calculating the motion of the mesh. It's just not moving the mesh. And that's just to do with the way the mathematics work. So you're doing an integration over this initial volume rather than the final one. So that's why you don't move the mesh. I've just put in the slides here. I can kind of skip through it, but just some notes on stress. Sometimes people get confused between all the components and the definition of equivalent stress, or AKA the von Mises stress as well. Typically, this von Mises stress in solids, it's checked if you want to know if something's going to break or yield. You check if the von Mises stress has reached the strength. So if you Google the strength of whatever material you have, if the von Mises stress, say if your steel is approaching the strength, then it suggests it's going to start to permanently deform anyhow. Whether that's breaking or plasticity depends on your material. Also, the maximum principal stresses are used. In solids4Foam, they are not generated by default, but there's a function object to do it. But typically, these two are the values to look at. Also, if you're a fluids person, strain is not something you're normally thinking about. It's mostly strain rate. So strain is it's just normalized displacement. So if we take this blue square, if I just change its length in this direction, it's just the displacement in this direction, just divided by the original length. So it's a normalized displacement. So in the same way, stress is a normalized force. Strain is just normalized displacement. So if you have a little square like this, you can strain it in this direction or this direction, or you can pull its top corner like that, and that's called a shear strain. And it's defined like this. So in fluids, you have your strain rate tensor, and this U represents velocity, whereas in solids, you have your strain itself, and this is displacement. These strains only make sense for small strain, but there's equivalent definitions, which I won't go into now, for large strain or finite strain. So what does a solids4Foam test case look like? So it looks like a normal OpenFOAM case, but there's just a couple of differences. So in this case, we have D and T are our solution fields in 0. We've all run all clean scripts, nothing strange there, just an OpenFOAM case. In constant, solids4Foam always expects there to be a dynamic mesh tick, so all the solid models are assuming it's dynamic mesh. All the solid models will include gravity. You can set it to 0 if you want. Mechanical properties, we'll look at that further. That's where you define this constitutive law. So like I said before, in fluids, the turbulence model is the critical thing, whereas in solids, the mechanical model or the constitutive model is the critical thing. So when we compare it to what happens in real life physical solids, if our answers don't agree, it's apart from the numerical schemes, it's mostly because we can't describe the definition of stress as well as we like. Some differences. Boundary conditions, I'm going to skip over that. I'm going to go back and open up the case and we can look through it. So I'm just going to focus on constant first. So there's this physics property. So this is a new file. So this file always has to exist for solids4Foam solver. So this is the first thing it looks for after the control loop. So it's just a short dictionary, and it's just, you set type solid or type fluid or type fluid solid interaction. So this is how the solids4Foam solver knows what type of simulation it is, the solid fluid or fluid solid interaction. And so that always needs to exist. If you specify a solid, then it will look for a file called solid properties. If you specify in physics properties a fluid, then it will look for fluid properties dictionary. If you specify FSI, then it will look for an FSI properties dictionary. Within these solid properties or fluid properties or FSI properties, there's settings to do with the solution of the governing equations. So in our test case, we have a solid problem, and then the solid model defines essentially what kind of solver is used. So we're using this thermal linear geometry. It has some settings. All of these default to reasonable values, so you normally don't have to set anything. So we're using this thermal linear geometry. Thermal because we're solving for temperature, linear geometry because it's small strain. So that's what this is saying here, thermal linear geometry. And here's giving a simple definition of of linear geometry in small strain. I know I'm going a bit fast through some of these textier slides, but these slides are also going to operate more as a reference for anyone wanting to go back over this. The mechanical properties file, which we can open and have a look at. There's only one material. Its type is thermolinear elastic, so that's this mechanical law implementing this definition of stress. You can see I've used the word steel here. That word, when there's only one material, that word's not used for anything. It's just for your own sake, just a label. But if you have two or more materials defined here, then this word will reference what the name of the cell zone is that this material should be assigned to. So if I have steel and aluminium, then solids4Foam will look for a cell zone called steel in your mesh and a cell zone called aluminium in your mesh. And for any cells which are in the steel one, they'll get this material, and any ones in the cell zone aluminium will get the aluminium one. So when there's only one material, it doesn't matter what you call it. But when there's more than one, you need corresponding cell zones. So like a normal linear elastic material, you specify Young's modulus and Poisson's ratio. So Young's modulus is stiffness. Poisson's ratio is how much it contracts in the other directions. 0.5 would be incompressible, so generally we use a compressible approach. And these are your thermomechanical parameters, so coefficient of linear expansion and a reference temperature. My box does seem to go move, doesn't line up anymore when I updated my Mac. In thermal properties, it's just, there's only one option, so it's just Fourier's law. So you can specify conductivity and specific heat. As I said, dynamic mesh state always needs to be specified. Here we're using static FE mesh, which is basically just a normal not moving mesh. And gravity is set to 0, but we can try turn it on and see what effect it has. If I go back to the case, and let me just remove the results. So if I open up the D file, the boundary conditions, and then some comments to make. So we have 3 symmetry planes. So we can use just type symmetry plane. That's what you would be used to. Or type symmetry, I think, in the Open Foam Foundation and ESI versions. So why have I implemented something called solid symmetry? Well, non-orthogonal correction is not implemented on boundaries in Open Foam by default in all the main versions of Open Foam, as far as I'm aware. That can mess things up if you don't have perfect, let's say, boundary layers. So here I've just implemented non-orthogonal correction in all boundary conditions used with solids4Foam, because it does have a major effect, in fact, on solids. So generally just use solid symmetry. If the mesh is perfect, then it won't make a difference. You can try yourself, but this will fix any of these boundary related errors. We have the inside and outside of the pressure vessel. So the inside, I'm using something called solid traction. So solid traction can be specified in multiple different ways. So you can specify a traction, which is a vector. So it's a force per unit area to apply to each face. You can also specify a pressure. So you can see both of these are using solid traction, but slightly different ways. Pressure is a scalar. This is not hydrostatic pressure, though. This is the normal component of the stress tensor. So they don't have to be the same. So the total traction that gets applied in this case is this vector minus the normal times this scalar. So it adds both of these together. So these can both be constant in time, like here on the outside, we've set it to be 0, constant in time, or you can specify a pressure series. And here is given by an XY interpolation table. So if I split my screen, constant time versus pressure, you'll see on the right hand side here, the first column is time, so 0 seconds to 5 seconds. At 0 seconds, apply 0 pascals of pressure. At 5 seconds, apply 1 megapascal of pressure. And for any time in between, interpolate. This out of bounds thing, it's just what to do if you're trying to solve the time step before the first time or after the last time. So clamp just means take the closest time. So if we ran our simulation to 10 seconds, after 5, it would just hold it at 1e6. And in between, it linearly interpolates. So this is pretty flexible. If you want to specify any function, you can just do it with small enough increments. So you can have multiple increments here. So you can see we have a pressure series, and here we have a pressure. So if you try to specify pressure series and pressure, it will give an error. Similarly, you can do a traction series just like this, or a traction series and a pressure series. So either of these can be time varying. If I open the T file, it's using the same non-orthogonal correction for temperature. It's less important for temperature. And on the outside, we have a boundary condition called thermal convection. It's just a simple heating convection, Newton's law of cooling boundary condition. And on the inside, we just have a time varying temperature series. So this time versus temperature is specified in the same way as the time versus pressure. So time versus temperature. So from 0 to 5, it varies from 300 to 500. If I open up my physics properties, and you can see we just have solid specified. So then that means solid properties will be looked up. So you can see we have thermal linear geometry is our solid model. And then we have some settings associated with that, which I can come back to. There are also some other ones commented out, just example ones. So there's linear geometry, total displacement. So that's similar to this, except it doesn't solve for temperature. So if I set to that, it'll just ignore the temperature field and only solve without the thermal effects. There's weak thermal linear geometry. So that will do the same thing as thermal linear geometry, except instead of looping over the temperature displacement field within a time step, it just solves temperature once and displacement once. So it's weakly coupled. And if I open up gravity, you can see it's set to 0. So let's just set it to something to see what happens. Set it to -10 in the y direction. I will also set the pressure on the inside to 0. I'll leave the temperature. I'll run my solver again. I'll just do it for one time step to see what the results look like. So you can see it's printing out some residuals here. Yeah, it's finished. It's printed the time step. Go back to power view, rescale it, or refresh it, and open up my original case. So where is the y direction? The y direction is that way. So if I go to the next time step, I look at my, say, displacement field, rescale it. And if I rescale this here, oh, still expanding because of the temperature. Let me just turn off the temperature altogether. So if I go into solid models, and I'm just going to switch to solid model. So now the equations being solved are just the displacement equation, so the conservation of linear momentum. And I think this solid model should be okay. It might ask for some setting. Oh, so it's saying no T field found in memory or disk. So it's saying I'm trying to use the thermal linear elastic mechanical law. So my mechanical properties, I'm trying to use a law that requires temperature, but of course I'm not solving for T, so it doesn't exist. So I'll just use normal linear elastic. So now it solves. You can see there's less residuals printed out because there's no longer a temperature residual. So this is T and D, now this is just printing D. In a few slides time, I'll talk a little bit about what's been printed out, but essentially you can see it goes to a time step, and these particular solid models are performing outer iterations within each time step until convergence is achieved. So it's essentially solving the displacement equation with holding some terms explicit, and then it updates those and keeps iterating and iterating. So you can see it's taking quite a lot of iterations, but the idea is each iteration is relatively fast. That's a little bit different from what's done typically in finite element when they have a coupled solution method. There is a coupled solid model as well you can try out, but it's currently can't be used with all the material layers. Okay, so now let's look at our displacement field. So what we should see with our displacement field is greatest displacement at the top. So remember, gravity is acting down, so this is just trying to move down. So if I rescale just to see the deformation, you can see that when I play it in time, just under its own weight, it's kind of being squashed. So it kind of makes sense. And you can look at all your stresses and things like that. So in this case, the maximum von Mises stress or movement stress is on the inside here. So if this was half a pipe and it was flat and was getting squashed under its own weight, you would expect the inside here maybe would start to permanently form first or break first. Okay. So that's just running it. So now for the residuals that are printed out. So in general, solids4Foam prints out 3 types of residuals for solid models. So it prints out something it calls the res in green, something the rel res in red, and the mat res. So when you have T and D, you'll have 2 of each of these, 2 of the res and rel res. But when you've just D, you'll only have 1 of each of those. So the res is just the initial linear solver printed out by OpenFOAM. That's these 2 here. The relative residual is taking the temperature displacement field and subtracting the previous guess or iteration and then dividing by the maximum displacement in the domain or maximum temperature in the domain. And finding material residual is if you have a nonlinear material law, which we don't here, then it may also need to iterate. So if you have plasticity, nonlinear plasticity, it may also have to iterate to calculate the stress. So you have a residual for that. So the way the solver works, it always checks the material residual is satisfied first. Once that's satisfied, it will check the other 2 residuals. So why do I have 2 residuals? Well, a residual is just a measure of how much the solution is changing while you're iterating. But it's really critical how you pick the normalization factor, whether that would be correct or not. And it seems that there isn't really a robust way of doing that for every type of test case. So in some test cases, just the way the OpenFOAM initial residual solver is normalized, it seems like a case is not converged when it is. So for example, if you're solving for temperature and temperature is just 0 everywhere and all the boundary conditions are 0, then it's hard to calculate a normalization factor because it will be 0. So you might get a residual that's large and not changing, even though the case is converged. So just having 2 of them makes it a little bit more robust. At the end, it's just printing out the number of inner iterations required at each stage. So the tolerance for the green and the tolerance for the red is specified in our solid properties. So if we go back to constant solid properties, the solution tolerance here is specifying what tolerance the green ones have to hit, the OpenFOAM linear solver, and the alternative tolerance is the red ones. The material tolerance is defaults here as well, can also be specified. So first, it makes sure the material tolerance is hit, and then when they're hit, it'll try to hit both of the other ones. If one, either red or green, if either of them converges to 10 times tighter tolerance than specified here, then it'll also accept that as converged, even if the other one hasn't converged. So that's kind of a way to make it a little bit more robust. If you want to run in parallel, you can just copy a decomposed project like you would normally do, put it in the case, decompose the case, use the typical MPI run or whatever script is on your cluster, and then you can reconstruct it afterwards. For this test case, you might want to try it yourself. If you if you're refining a mesh to 4.8 million cells, I've checked it on one of our clusters. It went up to just under 800 cores. So you can see that for this particular solid model, it's just getting the typical OpenFOAM scaling that you would normally get. Actually, it's probably a little bit better sometimes as well, because I think 300, I'm not sure what that is, but I think it's probably closer to 10,000 cells per core. So it's pretty good scaling. So you can see if you're running on 380 cores, this is an hour, so it takes about half an hour, where it takes about 24 hours if you're running on 6 cores. So you get good scaling and then this typical drop off. So some settings, we already looked at solid properties for controlling the residuals. Then you have the typical FE schemes and FE solutions. So this is just commenting on what we just saw. The other thing is the end corrector. So within each time step, this is it's not how many correctors are performed, but it's the maximum correctors that can be performed. So you saw in our case, it was doing maybe 500 outer iterations per time step, and the max was set to 10,000. So once it reaches it, it just jumps out. It's kind of like pimple control or something like that. Also, you can see it's only printing the residuals every 100 iterations. So if you printed them every one, you would just get, your log files would be very large. So it defaults to 100, but you can set that to any number. It also automatically prints out the last one. So even if you set it to 10,000, it'll just print the last one. FE schemes, we can have a look at that as well. So switching between transient and steady state, just in fluids, you can go between Euler and steady state for the d2dt squared. So you don't normally have this term in fluids, but in solids you do, because we're using displacement instead of velocity. So the second temporal derivative. So we can use Euler. Typically in finite elements, you'll use a Newmark scheme or trapezoidal or some blended scheme like that. And there isn't one included by default, even though I know quite a few people have been asking about it. So eventually someone will implement it and push it in. I guess I could do it if I have time at some point. So Euler is fine. It just, you might have, if a transient case with waving and bouncing, you might get energy, a lot of dissipation with Euler, just first order. Of course, there are explicit solvers implemented as well, in which case the time step's so small and it doesn't really matter if you're using Euler. The gradient scheme. You almost can never use Gauss linear for solids because you're always looking at the gradient of the velocity field or gradient of the displacement field, which tends to amplify errors. So if you use Gauss linear, this is on the standard plate hole case. So the mesh is kind of one block mesh there, one block and block mesh there, one there, and then one here and here. So where the cells change direction, you get these large spikes in discretization error. So Gauss, our least squares has no problem with that. So just always use least squares. You'll often see as well extended least squares 0 used in foam extend, and that's because it has the option to extend it least square stencil, which it's not using with 0, but it also implements non-orthogonal correction on the boundary, whether by accident or not, it does. So typically that one's used. The other schemes, these defaults are fine, and you almost never have to change them. Linear solvers, pretty similar to fluids. You can use multi-grid, but PCG generally is just robust and scales better. So normally these are the settings I leave with a relative tolerance 0.1. Because we're performing outer iterations until it converges, we can just always use a relatively larger relative tolerance. And we can relax our displacement equation or the field itself. Normally you don't need any relaxation. Maybe if your mesh is bad or you have large deformations or something like that, applying a bit of displacement relaxation tends to help. And very rarely, you might need equation relaxation, like in contact analysis, two things contacting. Sometimes if one's kind of floating in space and it's a steady state case, you might need a small amount of equation relaxation. For the fields, 0.1 is as low as you'll want to go, because less than that, it'll become very slow. For equation relaxation, it's very sensitive to displacement, how much you use here. So 0.99 seems like a very small amount of relaxation, but it actually has a measurable effect. So I'd never use less than 0.9. Even 0.9 itself will be probably too much. You'll end up with a displacement field that's almost 0 because it applies so much relaxation. Some of the code. So let's switch to the terminal for this. So that's my hot sphere case. If I run, it will reset some things I did, but changing the boundary conditions and things like that won't be fixed. So if you download it with Git, in case you're not an expert in Git, you can just reset the current directory back to its latest commit. just by using the command git checkout dot would do the current directory. So if you've messed up a tutorial in some way, you can just use that to reset a folder or multiple folders, or even just a file. Okay, there's some other cases as well you might want to check out in this term before I go to look at the code, like slab cooling is just a big block that's cooling down. There's one feature in this that's not well advertised. So if you go to solid properties, there's something called cell displacements, which is an option in most of the solid models. So if, for example, you have a block just floating in space, if you try to solve that steady state, it can just float off. So if you have forces on it or the block is just cooling down, it might just float away because the rigid translation is not constrained. So in finite elements, you might just pick a node and set the displacement of that node to be 0. So you can do the same thing in solids4Foam, except it's a cell. So you can specify the displacement of a cell. So you give an approximate coordinate, and then it will look for the closest cell center to this, and then you can specify the displacement. So you can do that for multiple cells, and also this displacement can be a displacement series. So if you want to specify time varying, you can do that as well. So that's important in that case. And let me go look at the code. So I'm going to go back to the main high-level solids4Foam directory. And I'm going to go first into applications, solvers, solids4Foam, solids4Foam.c. So here's the solver. So looks like a normal OpenFOAM solver, create time, set root case, create time. This is just writing out a header and asking for some citations. So there's no create fields. So instead we make something called a physics model. So if you're not down with runtime selection in OpenFOAM, this is just how we do it. So this is how we can, we're using a pointer or a smart pointer here, just to generate a physics model. So this physics model will go look, so this could be a solid or a fluid solid interaction model based on that physics properties ticked. So that's what this physics object is. Then it goes into the time loop. For each physics model, it's expected that they have a time step set or have a number of functions. So they have the option to set the time step. If that's not implemented, it just won't change the time step. It goes to next time step. You see there's physics.evolve. So this evolve function is the one that solves the equation. So that's where the main chunk of the time loop in the solver is. You also have a kind of end of time step function called update total fields. So most of the solid, fluid, and FSI models don't use this for anything, but it's there. And there's also a write fields function. So if there's some post-processing fields you want to create inside your solid or fluid or FSI model, it can be done there. And then there's an end function as well, just to let them know the simulation is at the end in case they need to do something. So you can see there's not much here. It's all inside this evolve function. So if I go into my SRC library in this top level and solids4Foam, so I'll see I have a physics model here. So that's an abstract base class. So solid models, if I tap in here, you can see all the different implemented solid models. So I have some coupled ones, some explicit ones, anything with linear geometry means small strain, anything with nonlinear geometry means large strain. Power loss is that's the thermal one. There's some other things as well. This UNS is just a different discretization. So the gradients in these UNS solvers are calculated using the face Gauss method. So it tends to be more accurate on unstructured meshes. So it's just a different way to calculate the gradient. You can do the same thing in fluids as well. So which one are we using? We were using two of them. We use thermal lin geometry solid and we use lin geom total disp. So I might actually start with lin geom total disp because it's just a subset of the other one. So if I open up this class and I go to the evolve function, so this is what gets called by, it's getting called because this lin geom total disp is a physics model. It's just a special case of a solid model. So I have this predictor option, we have a mesh loop. Also, you'll see in solids4Foam, rather than having different branches for different versions of OpenFOAM, we're just using compiler directives. So there's some flags that we define in make options. So for example, if it's OpenFOAM ESI or OpenFOAM Foundation, we have this flag to check. So for storing residuals, you can see it's done this way in the official OpenFOAMs and this way in Foam Extend. So that's how we port the code. In general, this looks a bit ugly. So the ideal is to try and minimize where this is done. So then we had an outside loop, which is a mesh update loop. So if you have some dynamic mesh in the solid, like there's a cracker mesh used in the fracture tutorial, so it splits, fractures can propagate. Then it needs to loop over your equation. So when it's a segregated solver, it performs this outer loop over the displacement equation. So this is mass by acceleration per unit volume on the left-hand side. On the right-hand side, we have sum of the surface forces and gravity. And then we also add a stabilization term, or the option to add one, which is like reach out or one of those techniques, just so we don't get checkerboarding, which OpenFOAM does in many cases, or is inspired by in many cases. And this plus Laplacian minus Laplacian implicit explicit is kind of a trick we use to use a segregated solution algorithm for solids. The idea is it's basically this divergence of stress, the sum of the surface forces. We just approximate that as the Laplacian, and then we explicitly correct for the difference between them and iterate until it converges. So when this loop converges, these two cancel out exactly. We have the option to relax the equation. We have the option to constrain certain cell points. We solve it. We have the option to relax the field. There's a function for that because you can use methods like Atkins to relax the displacement field. We're solving for D here. So we'll just update DD since we didn't solve for it. We'll just update DD. We update the gradient. That's actually done in this mechanical class just because when you have multiple materials, say a face is shared by, it has a stiff material on one side and a flexible one on the other side, then you'll get a discontinuity in the gradient. So you need to use some special technique to calculate the gradient near this interface. Kind of like in multi-phase fluids, you have to be careful calculating gradients when there's discontinuities in the solution field. And then this mechanical.correct, this is where the runtime selecting material law is called. So you can see the definition of stress is not in this code, it's called here. So that can be runtime selectable. Then we check if it's converged, and afterwards we might interpolate the D field to the points, and update these point fields and calculate the velocity as well. So that's it. If we go to the thermal one, go to the evolve function. It's basically the same thing, except now we solve the temperature equation first. So we solve the temperature equation and then the D equation. Okay, let's keep going. I know I'm spending a lot of time on solids, and many of you are here to hear about FSI, but once you just understand the structure of solids4Foam, then it's pretty quick to understand how to do FSI and fluids. So this is just going through examining the code like we did for solids4Foam. This is the general structure. I know I'm going very quickly, but once again, I said this is just for reference. There's multiple fluid models implemented, solid models, FSI, like we commented on before. You can open the code, look at where the equations are solved. This stabilization term, I'll skip over that now, but you can come back to me. You can ask a question if you're interested in it, but we're using reach out by default. There's also this Jameson-Schmidt-Turco fourth order method implemented as well, which basically does the same thing. We can also look at the mechanical laws. I won't open them now, but you can see how the stress is calculated. There's a correct function. You can see the definition of stress. So in this case, it was using the linear elastic law, and then it just adds on the thermal term. And then in the linear elastic law, it calculates the strain, whether if it's an incremental solver, it does like this. If it's total displacement, it does like this. And then calculates the stress here. If we time at the end, we we can look at other solids cases, but there's many solid cases. If you just go in and try them out, many of them are from published papers, so you can find them described there. But you can try contact analysis and check the order of accuracy, etc. Viscoelasticity, and box-plate limitation, elastoplasticity, so a permanent deformation. Often Abacus is my go-to finite solver, so I often just benchmark them against Abacus. You can go to large strain. I'm involved in a number of projects. Oh, this video, I think since I updated my Mac, isn't working, but it was working in an earlier slide, just squashes it fully. I have a number of projects with metal forming companies, so this is some of the general methods that are coming out of that for large deformations of metals. These videos are not working. It's not too exciting. So then, just to show if you wanted to do a fluid case. So this is your standard case from Furtzer and pH of a cylinder in a channel, and what your expected results are. Now I won't go through the theory. Once again, this is just for reference. You have your Navier-Stokes equation being solved. In this case, we're using the piezo algorithm, but you could use Pimple or coupled or whatever else you want. So the important thing here is just to note the difference between solids and fluids in solids4Foam. So there's essentially only one difference. So in physics properties, we'll specify fluid instead of solid. And because we do that, it will look for a fluid property file as opposed to a solid property. So there's almost no settings set in the fluids properties apart from I want to use icofluid or piezo fluid or interfluid. And because it will look up the settings where icofoam would normally look them up. So like piezo settings are looked up in FE solution, for example. So there's not many settings to set in this fluid properties apart from which fluid solver you want to use. Obviously, some of them aren't ported, but if you're okay with coding, it's easy enough to port them. You can just look at the other examples. So the code, this is where you can look it up. There's not many fluid cases, but for example, multi-phase interfoam and waves to foam is ported. So if you want to play with that, you can try that out as well. Okay, so FSI. And the first test case we're going to look at is just beam in a cross flow. So it's the picture behind my head. So we have a flexible beam in a channel. So this is a wall. We have a symmetry plane, ground, and we have a flow coming in here, some sort of parabolic flow. For this case, we have an incompressible fluid. This is just some of the settings to do with how the parabolic flow is at the inlet is being ramped up, the velocity in time. We expect this beam to bend back and might flex in some way. There's also a test case you can check out where we have an oscillating beam. So just the inlet is oscillating back and forth, the velocity. So in addition to the solid and fluid equations, we also have to enforce the interface conditions. So the velocity of the solid and fluid have to be the same either side, and the displacement, and the traction or the force. This can be done partition, which is what's implemented in solids4Foam, or you can do monolithic. So this is something people have tried this in OpenFoam already, but there's some papers on it, but there's problems with this approach. But I think people will continue to try work on this, and we'll eventually get a working version. Okay, now to go to the test case. So the difference is, this is just commenting on the solution algorithm. I'm going to skip over this just for your reference. I'm talking about in parallel. Okay, so the difference is, so you should be able to figure it out from before, except from one other difference. So in physics properties, we set it to fluid-solid interaction. That will force a FSI properties dictionary to be read. And then the last difference is the fluid and solid case are stored in subregions in the case. So instead of the solid boundary conditions being in 0, they're inside 0 solid. And the fluid boundary conditions are in 0 fluid. and initial conditions. The fluid mesh is in constant fluid, the solid mesh in constant solid. The system settings, system fluid, system solid. So that's the only difference. So we have a full solid case here, a full solid fluid case there. Inside FSI properties, we can specify this coupling procedure and some coupling settings as well. So let me just go to the case now and run it. So if I go back to my tutorials, fluid solid interaction, some other cases like this toric benchmark case, 3D tube, flexible dam break as well is kind of fun one to look at. So beam and cross flow, and there's a few of them, so I'll go linear elastic beam and cross flow. We'll just start that running. So I'll open a second terminal. Actually, no, I don't need to. I'll just put that in the background. So I have the first time step now. I'll just open Power View. So when you open this in Power View, you have a fluid mesh and a solid mesh. So when you press apply, both meshes are loaded. So you can see P is partial pressure because it's only in the fluid. It's not defined in the solid. So normally what I do is I open this case a second time. So if I go, let me see if I can remember where I stored this. And here, tutorials. Plastic beam, beam cross flow. Oh, my computer's struggling to run Zoom at the same time. Okay, here we go. So if I open up this case.foam a second time, so I'm opening the case twice. So in the first one, I'll only open the fluid. So I'll turn off the solid mesh. And in the second one, I'll only open the solid, turn off the fluid mesh. So I might rename this the fluid and solid. Oop. So now you can see I can apply the settings separately on each one. So if I just refresh both of these, I skip down a bit. So if I look at the velocity field and fluid, you can see it's coming in here. You can see the solid is moving. So let's turn on the solid. So once again, this is a small strain solid, so it doesn't move the mesh. Let's turn on the mesh. So you can see the solid looks like it's not moving, but it is calculating the motion and passing that to the fluid. So we just need to warp the solid. So if I warp it by the displacement field, multiplied exactly by 1, then you'll see it all lines up fine, assuming that they're both refreshed at the same time step. So if I play this now, you can see the solid moving and it shows the displacement in the solid. And you can play around with your Power View to make it look nice, maybe make the fluid translucent or make some slices or whatever you're interested in. Okay, so you can see the solid moving. Inside streamlines, etc. So you can see it's running, and I think it only runs to time of 4 or 5. So a couple of comments. There's loads of information in these slides, so you should be able to follow along. Some comments on the residuals, how they're printed out for the fluid and the solid and the FSI. How to run in parallel, you have to decompose both the solid and the fluid. You don't need global phase zones, and that's dealt with within the code, even though older versions of the code did. And I've also put some tips here if you're finding you're not sure what settings for the FSI to do, or you're having certain problems. I've noted these here as well. The end of this slide just goes through some of the code as well. So I'm conscious of, I want to allow some time for questions. So I will stop there. And well done if you stuck with me through all these slides. I know I was going pretty quick, especially near the end. But hopefully you found it interesting. And if you have any questions, I'm happy to answer. And if we run out of time with questions, I'm happy to answer directly if you email me afterwards, or if you wanted to have a chat via Zoom afterwards, that's fine too. So great.
That's pretty good presentation. I think we do have a couple of questions. Can you see the chat.
I will.
I can read it to you.
Let me see.
If you go back to about time 9:00, let's see, 9:04.
Chat here.
There's a time. So 9:04 is the first batch of questions.
9:04. Oh, mine are all in my local time. So 9:04.
Oh, okay, I'm sorry.
2:04. Yeah, 2:04.
Okay. So for the interest of time, we have like 10 minutes.
Yeah.
Maybe you can go down these questions quickly.
Sure. Great. So, okay, from Kutelmus, apologies for butchering your name. Many thanks for your contributions. How long do you plan to maintain solids4Foam? That's an interesting question. So I'm an assistant professor here in the university, and as of now, I'm planning on staying in the university. So the core of my research is numerical methods, and OpenFOAM is definitely one of the big tools I'm going to use. So solids4Foam is, I use it or a derived form of it in a number of projects. But I actually just am interested in it. So I plan to maintain this as long as, but not just maintain it, extend it as long as it's useful and interesting. So if something comes out and replaces OpenFOAM in 10 years time, then there's probably no point in maintaining it. But definitely for the next 5-10 years, I will maintain it. Any plans to ship it to as an OpenFOAM module? I know someone asked that on the forum and they gave a link. I just haven't followed up with it. The first step was I just wanted to port it to the official OpenFOAMs, which I've done. I still need to just finish off merging in some of the changes to do with the running to tutorials. So I'll definitely check that out. If you don't hear from me, follow up with me in 6 months. I'll follow up with that. It's not too much work. What's the most important limitation of solids4Foam? Probably at the moment, if you have very thin geometry, so if you try to Heron toric test case, it's really, really slow. And because the way the standard segregated solver in OpenFOAM, if you have very thin geometry in solids, it's very slow and inefficient to use a segregated solver. So a block coupled solver, I did work on that, implemented and shared it for small strings, and it's super fast, works really fast, but not for large deformations like in Heron toric. So I have some projects and funding applications in the works for trying to get someone to work on the block coupled for large strain. Once that's there, then that would be a really helpful thing. So that's probably the main limitation. Next one, Jack Hampson, 1912, 1-2, Hotspur tutorial crashes for me in PowerView. Okay, I will look at that. 1912 was someone asked me maybe 2 weeks ago, so it was 1812 is the main one I was checking on. So apologies, I can check that. I have a Docker of all of these, so the test passed. So when I pushed it, I run a test on the tutorial suite just to check they run. But why is PowerView crashing? I suggest if you move your 0 directory, just rename it to _0, and then create an empty 0 directory, and then try it. There might be something in the 0 directory messing with it. Or if not, take your 1 result, maybe delete all the time steps except for 1, make a new 1 directory and copy in just 1 field, like the D field. Maybe not the D field, actually, say the signal field. Open it then, see if that works, and keep copying in 1 field after another. My guess is if there's something in a D boundary condition, PowerView is confused by the size of what it is. That's OpenFOAM 19 must be printing out a different size or in a different format or something. Inconsistent patch and patch field types. Oh, sorry, if I just read the end of your comment. Patch and patch field types. Yes, actually, so this is because OpenFOAM 19 requires a couple of small changes to the case to get it to run. So there is a branch called port, a public branch called port OpenFOAM. I think you'll see commits in the last few weeks. So I've added an extra line in the all run script which will fix this error. I'd hope to have it merged by today's training. I didn't have time, so that will fix it. So sorry for that. Hauger, hello Hauger. Thanks, Philip. Is there a counterpart of the DSCL in the solid part? How do we preserve the volume when moving solid mesh? That's a good question. So in solids, when we're using, most of the solid models are using the Lagrangian approach. So under the Lagrangian approach, the motion of the mesh is a function of the solution. So the displacement at the cell centers, the motion of the points is not separate from that. So you can't move the mesh separately from your solution field. It just comes from the solution itself. So if you're using a small strain approach, you don't move the mesh, so you don't have to worry about that. And if you're using a total Lagrangian approach, this is one type of large strain approach. You also don't move the mesh. You just use mathematical mappings at the cell centers. So that's how it's automatically satisfied. When you come to an updated Lagrangian approach, that's where you move the mesh at the end of each time step by interpolating the displacement field to the points. Then, yes, you can add some errors there. So that's one thing that's one difference between finite element and finite volume. If you go to move the mesh in like an updated Lagrangian method, you have the displacements at the vertices in finite element where you have to interpolate them in finite volume. So you have to be careful how you do that. So you can introduce some errors. Though generally, I haven't noticed that they've messed with the solution in any major way. But yeah, interesting question. Thomas, nonlinear elasticity, solids4Foam evolution displacement by implicit, explicit, which is derived linear elastic. What do you think the solid can be used accurately? So accuracy, so I guess for numerical methods, we have accuracy, robustness, efficiency. So is it accurate? If you get your solver to converge, then solids4Foam is accurate. So it's essentially, you can think of it like if you're familiar with finite element, it's like a linear finite element scheme. It's a little bit better because the stresses are second order and the displacements, whereas in finite element, normal linear schemes, the stresses are only first order. So it's a little bit better. So you can check in there's references in literature and at the end of these slides where people compare, and it's pretty much as accurate as like finite element linear elements. So for large strains, so recently, and there's going to be a talk there's a PhD student, a visiting one, Iago, I'm not sure if you're here, he's presenting on implementation of Mooney-Rivlin, hyperelasticity, incompressible hyperelasticity, someday, tomorrow maybe, or Wednesday, I can't remember, or Thursday. So he benchmarked it, the accuracy is fine, there's no problem with that. In terms of efficiency and robustness, efficiency, it seems pretty fast. I think it's similar to Abacus. Robustness, depends on your definition of robustness. So I guess for bad meshes, it seems to work okay. It's similar to finite element in my experience. So what's the limit in this approximation? So there's no limit in accuracy if you get to converge. The only limit might be if you have very large deformations, maybe convergence could be difficult, and maybe a coupled solution methodology might help speed it up. So like a Newton-Raphson method or something like that, that might help if you're using this implicit explicit scheme. There are solid models I didn't talk about here implemented, like a fully explicit ones, which don't have convergence issues, but are slower, I guess. Andre, have there been applications with the immersed boundary method? So there is, in the 4.1 version, there's overset pimple fluid. So I know Željko had tried to do this. I know he did the flow in a channel. Actually, the tutorial flow in a channel is included with overset. So overset is similar to immersed boundary. So we can, I know Željko tried it with the actual immersed boundary method in foam extend, but the overset one is included. So you can try that. I'm not sure, I'll leave it to someone else to discuss how good overset is in foam extend at the moment. I know there's multiple implementations around, but yes, it can be used. Decomposed scheme you achieved for the best speed up for FSI. Lufang. Hi, Lufang. I'm not sure. I'm not sure. Typically, I just use Scotch or Metas, and I don't check that much. I know you're going to be limited by the speed of the size of the interface, because the interface gets constructed or assembled on, the full interface gets assembled on every core in parallel. So that is a bit of an inefficiency, but any of the scheme, I guess Metis or Scotch works probably best. Saber, I'm not sure, apologies once again. It's been a real challenge of me pronouncing names. Thanks for presentation. Recommendations, transient FSI with large deformations. Solid and dynamic early is choosing as major effect. You see a jump in deformation solid patch after zooming simulation stop. I'm not sure the reason. Okay, so a couple of questions. Recommendations for transient FSI. So it depends on the type of case you have. Typically for the large strain solids, the updated Lagrangian, nonlinear updated Lagrangian, or UNS nonlinear updated Lagrangian typically converge the best. You might need some relaxation factors with the field, maybe like 0.5. down to 0.5 probably with the D field itself if you're struggling with the solid conversion. So at FSI, you have to check if the solid converges, you have to check if the fluid converges. If they're both converging, then you have to check the FSI scheme converges. So if that's a problem, the FSI scheme itself, then maybe you need to start with the coupling turned off, like in the Frontori case, and then turn it on once the flow stabilizes. And you might also want to start with a very small under-relaxation factor with Atkin, and then let it converge with the IQ, INLS. Large deformations, and then you see a jump on restarts. So actually, yeah, there's a fix. I don't know if it's in one of the other branches, but when it restarts, some of the fields aren't written out, so the convergence maybe slows down when you restart for the solid. But if you have a case and a link, send me a link on the forum. Maybe you can describe it, and I'm happy to read it and see when you've specifics if I can help. Okay, 3 o'clock. No more questions?
Okay, the time is about 10 o'clock. So, well, here, Eastern time.
Yeah, 3 p.m. here. Yeah.
So thank you, Philip. This is an excellent talk, and I'm sure there's going to be more interesting things going to coming along the way down the road. And thank you for everybody coming to this session. Take a 15 minutes break, and then you're welcome to other interesting talks in 10:15. And thanks again, Philip. Right, and good luck for your future development of this.
Great, thanks everybody for listening. All the best.
Bye.